Hello and welcome to VHDL lectures. My name is Najim Lawal and now we shall be discussing VHDL extras. Here is the outline for today's discussion. Mainly we will be focusing on Finite State Machine with DATAPATH, how to design this, and we will go through some examples around Finite State Machine with DATAPATH. Essentially, components in digital design will have a control path and data path. The control path is usually captured as finite state machine so that we can have an organized center point of how to debug and know the status or the state of our execution or implementation. And of course, we need to have data path such that we can have optimized usage of resources, for example, adders, multipliers, comparators, allos, so that we will be able to have dedicated data crunching or mathematical function or algorithm that implement a particular function. So often a design will contain most of these things, finite state machine and data path, and we need to be able to synchronize them, and we need to be able to implement both of them together in a very useful design. And for this we need finite state machine with data path as an aggregation of data path and control units. Here is an example of this aggregation, in which case we have control units capturing finite state machine on one side, and we have the data part capturing the implementation of some complex arithmetic or mathematics on the other side. And the exchange of status between these components are usually done through control signals and status signals. So when these things are combined together from an external look, they look like a finite state machine with data part, with data coming in and control inputs coming out, and data going out and control inputs going out. Here is an example of finite state machine with data part, in which case we like to compute a function y as a function of x and two constants a and b. So if we have this function, the execution says that we probably have a clock and a signal to tell us when to start the operation, and perhaps we like to give a feedback that says that we are busy right now, we cannot take any more of this operation, and when the busy signal goes down, then the signal or the output y is ready. So we can have, for this kind of example, some input control signals that says start, reset, clock, and we can have a data input like a D, and we can have a data output like Y, status output like busy, which indicates that we are still computing and we cannot take any more instruction. So the waveform below perhaps shows a typical example in which we have a start signal saying that this is the start of the operation, in which at this value of start, when the start signal is high upon the rising edge of the clock, it means that the data A is also available. Subsequent values of the data D of values on the input signal D will be representing X and B. And when we get this signal start, it means that we can immediately eject our signal busy so that we don't get multiple starts in a row. And of course, according to this waveform, when the signal busy is driven low by our implementation, it also means that our output signal Y is available. So here is the design, a function y which can be implemented as a.x plus b, and then here is the interface to this function where we have a d on the inputs as the input signal, inputs control signal start, input control signal reset, and the clock signal CLK, the output signal data signal Y, and then output control signal busy is available. These are the signals that are available on the entity of this implementation. So when we implement this, it means that we can actually break the finite state machine with DATAPATH into two. On one side we have control unit, on the other side we have the DATAPATH. To implement the control unit independent of the DATAPATH, we only need two signals coming in and one signal going out. We also have some other control signals that are being emitted from the control unit into the DATAPATH to control the operation of the DATAPATH. So we have reset, we have start, we have busy, which are reflected on the main entity, whereas in the DATAPATH we simply have data coming in as D and data going out as Y, and some control signal to tell the DATAPATH what to multiply and perhaps where to store it. So here is the control signal on the input, control signal on the output, data signals on the input and output to the DATAPATH, and internal control signal that are being emitted from the control unit to the DATAPATH. Here is an example implementation of the finite state machine with DATAPATH that we are currently examining. It means that in this state we have 4 states: state start, state get A, state multiply X and A and X, and state add D, B to the multiplication, and of course we go back into the starting state when all these operations are completed. And of course it means that while we are in state start, we can go into the next state only when the start input signal is high. And while we are in this state, it means that we can actually emit the busy signal to 0, which means we are not busy, not doing anything right now. We send to the DATAPATH, store A is 0 and store product or multiplication is 0, because there is nothing to store, there is nothing to multiply, and that we are not in any way busy. So when the input signal is high, the input start signal is high, then we can go into the next state of get A, and immediately we go into this state, we can emit the busy signal as being high, and we can tell the DATAPATH to store the input signal, the data on the input signal D, into a register called store A. So we emit this control signal to store A, and immediately on the next clock cycle, it means that we can still emit the busy signal as being high because we are busy right now, and that we are no longer storing A, but now we are going to store the product of A and X. And of course, on the next clock cycle, the data that will be available on the input bus D is B, so we can add this data to the product of A and X. So after all this is done, we are still emitting busy signal to be 1, and we are no longer storing A, we are no longer multiplying A and X, but rather we are immediately adding B to the product of A and X. When all these are done, we go back into the start state, and at that point we emit the signal busy to be equal to 0, which means we are no longer busy. And here is the DATAPATH, in which case when it's full of registers, a multiplication box and an adder, and here it means that we only have one input data bus and we have one output signal Y. But how to interpret this data bus, whether to interpret it as an A or as an X or as a B, is controlled by the extra input control signals store A and store PR. So when store A comes in as high, it means that the input data is A and it should be stored into a register. At the next clock cycle, the input data will be X and it should be multiplied. When the results are available, then it means that immediately we get the store product, which means that this result should be stored in a register, and upon the next clock cycle the input signal will be B, and here we can directly add and then we get the result. So here efficiently we have been able to use one input bus D to represent three input signals A, X and B, and by changing some control signals store A and store PR can we efficiently make use of this data path in order to save resources, so we don't use unnecessarily a lot of data buses that will consume so much of energy during the implementation. This of course is based on the fact that this implementation is very efficient using sequential implementation and storage of the data and the multiplication and addition. So the summary here is that we have a data path that knows how to compute an output as an aggregation of logical operation, arithmetic operations, multipliers, adders, greater than and equal to, square root functions, and some other algorithms. But then we also have a control path which is based on our knowledge of finite state machine, and we can use this knowledge of finite state machine to optimize the execution of the data path in order to fulfill a given algorithm. So a very good implementation will say that we need to identify which operations should go into the data path and which operations and which states will be needed in the control unit, and what are the signals that we need to exchange from the control to the data path, and what are the feedbacks that we need to send back from the data path to the control unit. We need to have very good background and very good knowledge in finite state machine design and implementation, and we need to be able to be familiar with the kind of computational logic block and arithmetic blocks that are available for us to use. With this, we've come to the end of our discussion of finite state machine with DATAPATH, the design and some examples. Thank you for joining us.